Alright, we're not going to go through all of the details about it because this really is a CCNP security type topic, but we're going to go through some of the basics of VPNs and some of the technologies behind it, encryption and data integrity, hashing and such. So start out with the basics here. VPN, it's a virtual private network. Now it says private network in the name, but it's really not private. It makes it sound like there's a magical tunnel that it creates, and it kind of is, but kind of isn't. So what it does is you take your data, you encrypt it according to your configuration that you use in your VPN config. It gets put out onto the public internet, and then it gets routed to its destination. And then on the other side, it then decrypts that data and then sends it to where it's supposed to go on that network. So that's really what a VPN does. You're sending your data still onto the public internet. It's still there for everyone to see. It's just scrambled because you're using encryption. So hopefully you're using a good level of encryption so that people can't read what your data is. So that's really what a VPN is. People refer to them as tunnels all the time, VPN tunnels, but it's not really it makes it sound like it's a super secure, like secret underground tunnel that you're using. You're just sending packets of data that are scrambled onto the public internet, and the configuration is referred to as the tunnel. So that's where that comes in. So really what it does is it allows for site-to-site communication, or remote access. So if you have two offices separated by some distance, or if you are at like a hotel or something like that, or at home and you need to get into work, that's really what the two use cases are. So site-to-site tunnels would be between usually two pieces of hardware, such as a firewall or a VPN concentrator, and a remote access is going to be between a client of some kind, like on a laptop or something like that, and your central device, which could again be like a firewall or something like that. It doesn't have to be. You can run these off of servers, such as Windows servers or Linux servers, that are publicly accessible. Not usually the most common way of doing it, but that is an option that is out there. Majority of people use some sort of firewall product from various vendors. So when you're doing either of these, you're going to be using a variety of different protocols. You have, for example, IPSec. You have, and we'll talk about some of these in more detail. You have SSL. There's L2TP and PPTP. So when you're using remote access, you'll probably be using IPSec or SSL, maybe one of the other ones. Site-to-site tunnel, you're probably using IPSec, or maybe the other two TPs, depending on what kind of devices it is. But I say the vast majority use IPSec and SSL, and that's usually that's it. There is native support in Windows and Mac and stuff for the TP versions, so sometimes tunnels are set up in that way so that you can use the native clients built into the operating systems. So VPNs are used because they are cheap, basically. It's more economical to buy several $100 firewall or several $1,000 firewall on each side, and then just set up a VPN tunnel between them, than paying a constant monthly fee towards some sort of service provider for a leased connection. Most likely you'll get much greater bandwidth on this as well, although you lose out on not having a committed information rate, and you don't have a committed quality of service. So neither of those are really provided with a VPN that's reliant on your internet connection from your provider on each side and how the internet's feeling that day. The original VPN protocol, it's not even a VPN protocol really, the original encapsulation protocol really that kind of started this whole thing is generic routing encapsulation, which is GRE, and we're going to actually do that as a configuration coming up. We don't really get into the VPN config in CCNA, but we do a GRE tunnel because GRE is a little special. It doesn't offer any authentication or encryption, but it does offer the ability to traverse different networks. So if you had some sort of network over here connected to a router, some network over here connected to a router, and then some sort of weird network in the middle that was a different protocol or something, if you want to get from this network to here, or if you wanted or this one, maybe this was like a conflicting IP scheme or something like that, you can get from point A to point B using a GRE tunnel. So that's what we'll do. So IPSec is really the main one that most people use. So we'll go into some of those details here. So IPSec does offer authentication and encryption. So that's why it's mostly used by most people. It's built into the name. It says it provides security for you. It provides that encryption. And there's different kinds that it provides. There's DES, there's triple DES, there's AES of different flavors. There's a number of different. Sometimes there's an RC4 or something. Depends on what people have set up. There's different modules of encryption algorithms that you can use, and we'll talk a bit more about those coming up. There's other algorithms that can be used as well, such as MD5 and SHA of various flavors, which can be used for data integrity, which we'll talk about. So it's kind of modular in that IPSec is the framework, and then you can pick and choose what you want to use within this. So IPSec provides, and provides all the things that GRE does not, basically. So it provides confidentiality, through those encryption algorithms, data integrity, through the different hashing algorithms that are out that we can choose from, such as MD5 or SHA. And this really is the same idea as having the frame check sequence or the CRC value in your packets and frames. It'll run it through a meat grinder on each side that I have used as the phrase before. It runs it through a meat grinder and it comes up with a value, and on each side it checks that value, and if the value is not what it expects, then it knows it's been manipulated in transit or it's corrupted or something like that. That's what the data integrity does. So it provides that ability. It also provides authentication. So am I talking to the correct endpoint? We can do that through a variety of ways, such as certificates or passwords. And it provides anti-replay protection. So if someone sends me the same piece of data, I know that and I'm going to ignore it. So as far as encryption algorithms go, there's a number of them, as I mentioned. So we'll write those out and I'll talk about those a little bit. You have DES. And these are like the most common ones. Sometimes you'll see others. There's DES, triple DES, and AES. And DES and triple DES, just a note, are considered not secure anymore. DES specifically so, because it's so much older. Triple DES is on the border. People should be switching away from it to AES. But we'll get into that as to the differences. So DES is a 56-bit symmetric encryption algorithm. Triple DES is a 168-bit symmetric encryption algorithm, and AES has 3 flavors you can choose from: 128, 192, and 256-bit symmetric encryption algorithm. So there are different types of encryption algorithms. I keep saying symmetric. So there is symmetric and asymmetric. So symmetric is more efficient and uses a shared key on each side. So you choose a password on each side, essentially. And this is what the majority of your data is sent and received using. So will use an asymmetric encryption algorithm, and that's what these bit values are referring to, the security level of that symmetric algorithm. The problem is, how do you get that shared key to the other side? Because you don't want people to see that shared key when it's in transit, when each side is trying to set up the tunnel. So you do that using an asymmetric algorithm, and an asymmetric algorithm uses one key to encrypt and one key to decrypt, hence the asymmetric definition of it. So it's more secure, and it's has a higher bit value. Often you'll see them referenced in like 2048 and 1024 and things like that for their bit values. And the problem is, though, that they are much slower because of this. These differences, they're much slower. So what really usually is done is you'll set up a VPN tunnel, and it'll use both. It'll use asymmetric to send the shared key in order to bring up the symmetric tunnel. So that's really what that does. So IKE will use an asymmetric algorithm to transmit the shared key so that IPSec can bring up the symmetric encryption of your choice, such as AES. And they kind of work in concert. And you can get into those details, through other means. For CCNA, we're just going to reference these basic details. So as I mentioned, DES and triple DES are now essentially considered insecure, and you should be moving to AES. AES is the advanced encryption standard, and it uses the Virgindel cipher. I hope I pronounced that right. I'm pretty sure it's Virgindel. Let me write this out. Virgindel cipher. And the way that worked was AES was created thanks to a contest run by the National Institute of Standard and Technology, NIST. Same people who do the time servers and the atomic clock and stuff like that, as well as many other things. So they ran a contest and said, we know that DES is going to be hackable soon, so send us your ciphers and we'll pick the best one. So Virgindel was the one that won, and that's what we use. And so there's different levels of that cipher that is now available, and it was named the Advanced Encryption Standard, so that's where AES comes from. So AES is highly secure. If you not consider any of the conspiracy about the NSA having backdoors and all that stuff, from a just purely mathematical standpoint, AES is such a highly secure algorithm, and it's also optimized, you could say, for modern hardware cryptography chips. So it's a much more preferred algorithm to use. It's more efficient in its methodology than running triple DES, for example. So that's one reason to use it as well. But AES is so secure, it's just crazy. For example, 128, the 128-bit version, could take upwards of 100 billion years to crack with brute force. That's not considering increase in powerful in computer performance over the years, and some other tricks you can use to try and hack it. If you just brute forced something, it would take around 100 billion years to crack, or more, kind of depends. And when you set up a tunnel, you can set it to rekey every 8 to 24 hours or something like that is usually what people do. So someone would have to crack that key that was shared within that 8 to 24 hour period on an algorithm that would take 100 billion years to crack. So just think about that for a second. So it's very, very secure. And of course, if you use some of the higher bit values, you'll get an additional level of security on top of that. So that's why it's suggested. It's just very, very secure. From a basic level, you can consider more bits as more secure, although it's not necessarily true. I like to use the higher bit levels and just, go for broke. There are times where you might not want to use the highest bit level available. Maybe you are, for some reason, trying to send voice over IP or video traffic from one location to another. Doing so over a highly encrypted VPN tunnel might not be the best idea because there's going to be more processing involved and it'll be a little bit slower. So in those kind of examples, it might be better to have a less encrypted tunnel or some sort of WAN link that you're leasing. So I mentioned the asymmetric algorithm, so I should probably mention that. So before we move on to other things, so IPSec uses these for symmetric options, and asymmetric is done through Diffie-Hellman. So the Diffie-Hellman groups is what they're called. Provide that asymmetric ability to transmit that shared key for a tunnel to come up. And you'll see them in groups such as group 5 or group 14. Sometimes they'll refer to them as the bit values. So you might see it as whatever bit value it might be, like I mentioned before. It really depends on the vendor. And some of the Diffie-Hellman groups are designed to work with certain encryption algorithms. So for example, Diffie-Hellman 5 and 14 are better used for AES. Diffie-Hellman group 2 is better used for like triple DES. Diffie-Hellman group 1 is better used for DES. They're kind of designed to work together. So do a little research on that when you go to set it up, so that you are being as efficient as possible. Something a lot of people don't think about. I often will use AES 256 with DH group 5 for 14, and that seems to work quite well. Alright, so from here we'll move on to data integrity, and we'll talk about that. And of course, I goofed up my layer, so give me a second here. We'll just erase it really fast. There we go, giant eraser. Alright, there we go. So the other piece of the puzzle is data integrity. So I mentioned that before as something that's provided. So data integrity is of course important. You want to make sure that what you send is not manipulated en route if someone's in the middle. And there's two common algorithms that are used that I think I mentioned before. Was MD5 and SHA. There are other ones out there, but MD5 is highly common. It's 128-bit, and it's unfortunately starting to be considered insecure due to work on hacking it. So a lot of people use SHA, and specifically you'll see it referred to as SHA-1, SHA-1, SHA-1. And that is 160-bit, so it's a little bit more secure. And there's also newer versions of SHA, so you can of course choose the even more secure version. There's 256-bit, there's a 384-bit, there's a 512-bit version, you can go hog wild there. And those offer that meat grinder functionality I mentioned. So we hash out the values and determine if the data is the same on each side when it's sent and transmitted, or sent and received. So my suggestion would to stick with one of the SHA flavors, whatever your vendor might support. Some of them only support SHA-1, that's fine. But if you can go with the higher values, that's great too. Again, more bits, slower it's going to be. Usually it's not a problem though for standard communications with TCP and such. So another thing we received from IPSec is authentication. So we do so through two ways usually, is a pre-shared key of some kind. So I mentioned that there's a shared key with symmetric algorithms. You'll define some sort of secret password on each side. That's one way of doing it. Or you can do certificates. So it's really up to you how you want to do it. The majority of people do pre-shared key though. Then our last piece of the puzzle is confidentiality. There's two different headers we can use in an IPsec tunnel. There's the authentication header, AH, and there's the encapsulating security payload, ESP. So if you use AH, it will authenticate but does not encrypt. If you do ESP, that will encrypt. I would say the vast majority of people use ESP so that you get that confidentiality since you're sending it across the internet. If you are using it within some sort of local network situation, you might want to use AH so you don't encrypt things, but even then I'd say that a large majority of people are going to stick with ESP. So if you see that, that's really what that is. It's more or less, do you want encryption or not? So that's the real basic way of saying it. IPsec, from a technical standpoint here, uses UDP 500. You also see people refer to IKE using UDP 500 or 4500 if you are using a NAT traversal. So you'll see NAT traversal. We'll often use that other port number. And both of those are unfortunately often blocked when you are out and about, going to hotels and such. So that's where the SSL comes in, and we'll talk about that in a minute. So for this level of connectivity, Cisco offers the Cisco EasyVPN client. Well, Cisco EasyVPN would be the config, and then they have the Cisco VPN client or EasyVPN client, whatever you want to call it. So that's a specialized piece of software you have to install. It'll end up adding some stuff into your IP stack, TCP IP stack in Windows, and you'll need to get that up and running on your client, and then you have to go in and add a profile and configure it so that it knows how to connect to the other VPN concentrator or firewall that you have. That's more involved, and usually the clients are a bit clunkier. I think they're a little bit larger and bloated almost. The newer methodology with SSL is usually a bit easier to set up and maintain. So we'll talk about that right now. Why not? So we have SSL as our second option for connectivity, and that is probably the best bet for remote access. So, if you're using regular IPsec, that's great for site-to-site tunnels, but when you want to do remote access, you're probably going to want to use SSL, at least in my opinion. So the clients are much smaller and thinner. They're easier to work with, and it uses TCP default 443, although you can change it. TCP 443, so that's the common port used for any SSL connection, HTTPS, when you're browsing the web and stuff. So hotels and different locations that try to block different ports that you can use, there are 99% chance they're not blocking port 443, so you can remote to where you need to using this, and you can kind of get around those situations. The clients, as I mentioned, are easier, and Cisco offers two different ways of doing so. They have the AnyConnect, a secure mobility client, which is a client that you have to install. So it's kind of like the VPN, regular VPN client, and then you have to configure that, of course. Or there's the mobility clientless. SSL VPN. And this actually works off of a web browser. Other vendors also do this. Usually they'll run it off of a web browser, or the web browser will then run the installer for you, pre-configured and things like that. So there's tricks that they use to make this easy for you. The vast majority, though, I'd say people will use this sort of setup, where you can just go to a website, you log in with some sort of credentials through your Active Directory domain or something like that, your LDAP domain, and then it'll authenticate you. It pops up and says, okay, install this package. If it's on using IE, a lot of times it'll load it through some sort of plugin, and then it'll just connect for you real nice and quickly. It's a real nice methodology for remote access. Makes it easier for a lot of people, and supportability is a lot easier, since it basically boils down to go to the website and click a link. It's a lot easier than setting up the VPN client, and you get those benefits of getting around some of the blocking that's done out there. So that's really the basics of VPN. I mean, that's like the real 30,000-foot view. So what we'll do is go into GRE tunnel config next, and we'll set up just a little VPN, little GRE tunnel, pretending we'll have to go across some sort of network in the middle.